In section 8.2, we're going to find the law of cosines. We're going to use the law of cosines to solve triangles. We're also going to determine whether the law of cosines or sines should be used to solve a triangle. In the last section, when we developed the law of sines, we used it to solve triangles that had two angles and one side. And we also used it to solve a triangle where you had two sides and you had an angle that was across from one of those sides. However, we're going to need more nifty tricks, like the law of cosines, to solve triangles where you have two sides but the angle is between, not across from one of the sides, or where you just have all three sides and don't know any of the angles. All right, so we're going to begin by looking at this triangle ABC, and we're going to imagine dropping down a hypotenuse out here, or a side that is going to be perpendicular to the x-axis out here, and that's going to form a right triangle right here. And we're going to be focused on this angle C initially for this triangle, for this orientation of the triangle. And the angle C is this angle inside the triangle, but we know that angle is referenced by this smaller angle outside, and that smaller angle is going to have the same sine and cosine values of the bigger triangle. All right. So if I look at this little triangle with this referenced by this big angle, I know that its cosine is going to be the side that is adjacent divided by the side that is the hypotenuse for this triangle. So that's going to give me a ratio of x over b. If I multiply b to the other side, x would be equal to b times the cosine of that angle C. Similarly, if I look at that angle again, the sine of that angle is going to equal the opposite over the hypotenuse. It's going to equal y over b. And so y itself would be equal to b times the sine of the angle C. So this point A right here, who had coordinates x and y, now has coordinates x, which is equal to b times the cosine of C, comma y, which is equal to b times the sine of C. Using the distance formula, looking now at the distance between points A and B here, we're going to use the distance formula to find the distance C squared here. And the point B is going to be an ordered pair that has A, comma 0 as its ordered pair. So the distance formula, we're going to subtract the x coordinates and square them, and then add the difference of the y coordinates and square them. Instead of x and y, we're going to be using this version that has x equal to b cosine C, y equal to b sine C. So the difference of the x coordinates would be, let's see, we're going to have b cosine C minus a quantity squared. And then we're going to add on y, which is b sine C minus 0 quantity squared. So we need to do a little bit of simplifying here. So in that first place, when we have that b cosine C minus a squared, we're going to multiply by itself to finish that square, to expand that square. So C squared is going to be equal to b cosine C times b cosine C, which is b squared cosine squared C. Then I'm going to have a negative AB cosine C from this grouping. And I'm going to get another negative AB cosine C from the other middle. So I'm going to have negative 2 of those, negative 2AB cosine C. And then last, we're going to get negative A times negative A, which is positive A squared. Then we come over to this piece here. B sine C minus 0 is just B sine C. And when I square that, we'll have plus B squared sine squared C. Okay, so the next piece to simplify this, we notice that we have two terms, the b squared cosine squared c and the b squared sine squared c, two terms there that have the b squared piece. Let's move those together and factor out b squared. So c squared is going to equal, say, b squared times cosine squared c plus sine squared c minus the 2ab cosine c plus the a squared. Once we've factored b squared out of those two, we factored that b squared. We've got our cosine squared c plus our sine squared c. We should recognize that as one of our Pythagorean identities. This is equal to 1 by one of our Pythagorean identities. And so we end up with c squared equals b squared minus 2ab cosine c plus a squared. A little bit more rearranging on that to move the a squared and the b squared both to the front gives this bottom line down here. C squared is equal to a squared plus b squared minus 2ab cosine c. That's where this comes from. Now, you could also make an argument that you could look at aligning a different side with the x-axis, just tipping your triangle, putting the x and y-axis in a different position, and doing this again. And you would come up with the other two formulas. So you also could write the formula as either a squared or b squared equals, in the case of a squared equals b squared plus c squared minus 2bc cosine a. What you want to notice from all of these formulas is that the angle that you are talking about is opposite of the side on the other side. So if you have the cosine of angle A, side A is on the other side, and the sides that are on the same side as that angle are the other sides, so B and C. Or in the case of C, A and B. All right, on the bottom here, let's notice what happens in the special case where C is the right angle. So if in this bottom row right here, if C is a right angle, 90 degrees, then we would be evaluating the cosine of 90 degrees there. And the cosine of 90 degrees is right here. The ordered pair for that is 0, 1. So the cosine of 90 degrees is 0, the x-coordinate. So if you have a right triangle at angle C, that would give c squared equals a squared plus b squared minus 0. And so that's the regular Pythagorean theorem. So the law of cosines here is an extension of the Pythagorean theorem, and using a right triangle simplifies it down to the Pythagorean theorem itself. This is the more general version of the theorem where the angle does not have to be 90 degrees. If it is, it generalizes or simplifies down to the Pythagorean theorem itself. So the law of cosines is a more general version of Pythagoras' theorem. And it works for any triangle, whether that angle C or A or B or either one of those is a right angle or not. It doesn't have to be, so it works in any case. All right. Taking a look at the next page, we're going to solve a side triangle. And when solving a triangle like this, where sides on either side of an angle are known, we're going to use the law of cosines to solve for the third side. And then we can use either law of sines or law of cosines to completely solve the triangle. Our first step is going to have to be the law of cosines. And then after that, it looks like we're going to get a choice if we use the law of sines or the law of cosines. Let's see why. In this triangle, we've got B, which has a measure of 133 3 degrees. So let me just draw a triangle that seems to have an angle that is obtuse here. So I'm going to make this my 133-degree angle B. And let's call this one angle A, just because it looks like I made it a little shorter. It's not to scale, that's okay. But side A is supposed to be a measure of 12 length, and side little c is supposed to have a measure of 15 for its length. So that's how my triangle is set up. Okay, so I know angle B, but I do not know side B, which is the side across from it. I have no pairing of a side to an angle. None of these do I know both the side and the angle in a pairing, which means that I cannot start with law of sines. I'm going to have to start with law of cosines, as we said here. The angle that I have is B, so I'm going to have to find side B using B squared equals A squared plus C squared minus 2AC cosine angle B. That's one of the versions of law of cosines. We have angle B. We're going to find side B using the law of cosines. Let's plug in our values. B squared is going to be equal to A, which is 12 squared, plus C, which is 15 squared, minus 2 times 12 times 15 times the cosine of 133 degrees. Okay, so let me get my calculator. To evaluate 12 squared plus 15 squared minus 2 times 12 times, that's supposed to be multiplication, so times 15 times, I need to do cosine of 133. I better make sure that I'm in degrees. I'm going to switch into degrees, and I'll do the cosine of 133 degrees. B squared is equal to about 614.52. So B will be equal to the square root of that. I'm just going to copy that number and paste it inside of my square root here. B is about 24.79 units long. All right. So I know the lengths of all of my sides. Let's write these down. A is length 12. B is length 24.79. And C is length 15. So I have all 3 sides. I need all 3 angles to completely solve this triangle. Now that I know side B, I do have a side angle pairing, so I would be able to set up a law of sines ratio and use that to solve for either angle A or angle C. So I can do that, or I could use another instance of law of cosines and solve for angle A or angle C that way. Let's go ahead and use the law of sines this first time, and maybe in the next example, we'll look at using the law of cosines. So let's use the law of sines to find angle A. So the sine of angle A divided by length of A, which is 12, is going to be equal to, I have to use B because that's the only one that I know the pairing of. So that's the sine of angle B, which is 133 degrees, over the length of B, which is 24.79. We're going to multiply that 12 over. So sine of A equals 12 times the sine of 133 over 24.79. 12 times the sine of 133 divided by that 24.79 gives us sine of A equals 0.354. And to find angle A, I'm going to take the arc sine, inverse sine function, And I'm going to go ahead and copy that value and paste it so I can just keep a few more decimal places on it. And I get an angle A of about 20.7 degrees, or, hang on a second, remember that we always have two possibilities when taking the arc sine of both sides. So if this angle is 20.7 degrees, this angle over here is shy of 180 by a measure of 20.7 degrees. So this would be 159.3. Okay, so let's go ahead and find angle C. So if A equals 20.7 degrees, then angle C, we're going to subtract from 180. So we've got 180 minus B, which is 133 degrees, minus the 20.7 degrees, gives us 180 minus 133 minus 20.7, gives us a measurement of 26.3 degrees, or if angle A is 159.3 degrees, then C, which would be 180 minus 133 minus 159, you can probably already see what's going to happen here. 180 minus 133 minus 159.3. It's definitely negative, right? So it equal a negative 112.3 degrees. So that means that this option is not possible. So we're not going to have that angle for A. So there's only one solution. Angle A is 20.7 degrees. Angle B is 133 degrees. And angle C comes out as 26.3 degrees. We will find that unlike the side angle case that can have multiple solutions, we're not going to have multiple solutions for any of the other situations. This is going to be the only one where multiple solutions are possible. And by multiple, I mean two. You can't have more than two. So two solutions possible for this type. Remember, we could have 1, 2, or 0 solutions possible for that type in the law of sines section. We're going to find that that's not the case in the others. And the reason is that once the three sides are known, the triangle size is fixed. And we're going to get that first side first. It's always going to come out that the other possible angle just doesn't work. Very good idea to demonstrate that as you're solving this, to make sure that we don't forget to check both angles. However, it's unlikely to work in this situation. Let's see how this works again in example 2. In example 2, I have a 30-degree angle. I have a side length B of 12 and a side length C of 24. So let's draw ourselves a triangle. Here I know that the angle A needs to be about 30 degrees. And then angles B and C, this right here is side little a. Just based on the way I've drawn them, it looks like I'm going to label this one as B with a measurement of 12, and this one is C as a measurement of 24. Again, if you plan ahead in drawing your triangle, you can try to make this side look twice as long as this side. I've got my labeling in here as such. And I don't have a pairing of an angle and a side again. The side that the only angle that I know is across from an unknown side. So I will have to start with the law of cosines to find that side. It's the only option. There's no pairing making law of sines possible as the first step. So we'll start here with a squared equals b squared plus c squared minus 2ac cosine of angle A. We're looking for A squared. B is 12, so 12 squared plus 24 squared minus 2 times 12 and 24, and the cosine of that 30-degree angle. The cosine of 30-degree angle is a known angle, but it's going to come out as square root of 3 over 2. This ordered pair would be root 3 over 2 comma 1/2. And so if I needed it exact, I could work with the root 3 over 2 here, but it's going to be messy. We're just going to go ahead and use the decimal version of it in this problem. And you know that if you did need to do it exactly, you could, but it's going to involve square roots of square roots, so it's a little messy. So we've got ourselves a 12 squared plus 24 squared minus the 2 times 12 times 24 times the cosine of 30. Should still be in degrees here from the last question. Still in degrees. I've got ourselves an A squared measure of 221.17. And if I take the square root of this value, let me copy that number. The square root of 221.17 comes out as 14.87. So I know all of the sides. Side A measures at 14.87. Side B measured at 12, and side C measured at 24. I need to know all 6 things, but once I know 3 sides or 3 angles, I just like to write those down, get them out of the way, and now know that I'm looking just for angles. Okay. Once again, let me get rid of decimals for a second. Once again, after I use law of sines to find that third side, I can use either law of sines or law of cosines to complete solving the triangle. I used law of sines last time, so just to see how it's going to look, let's go ahead and use law of cosines to find one of the missing angles. Doesn't matter which angle, so I'm going to say I want to find angle B. Let's say I find angle B here. So if I find angle B, I need to use the version that's going to have B as the missing angle. So that's going to be B squared equals A squared plus C squared minus 2AC cosine of angle B. Side B is 12. So 12 squared equals A squared. Side A is 14.87 squared plus side C, that's 24 squared, minus 2 times side A, that's 14.87 times side C, that's 24, and then the cosine of angle B. I have to get the cosine of angle B by itself, so I'm going to subtract these 2 values over. So let me just highlight and indicate that I'm going to subtract these 2 values over, and I'm going to do that in the calculator. So we'll take our 12 squared and we're going to subtract the 14.87 squared. I meant to type the 8, 14.87 squared. And we're also going to subtract the 24 squared. That's going to give us a negative 653.12 equals the negative 2 times 14.87 times 24 times the cosine of the angle B. And now it's going to be division. So we're going to now divide this piece off to solve for the cosine of B. So I will copy this value and divide it by negative 2 times 14.87 times 24. Hit the wrong key there at the last bit. Got an underscore here. Okay, so this comes out as 0.915. But for not b, that's for the cosine of b. So I'm going to need the inverse cosine function of both sides. We'll take the arc cosine of 0.915 to give us that angle B. Just copying and pasting to save myself some time on writing that value in. So my angle B is equal to about 23.79 degrees. Now I'd like to consider, similarly to what we did in the top when we did our law of sines, I'd like to consider the other possibility for angle B. The other possibility, according to cosine, if one of my angles is 23 degrees, remembering that cosine corresponds with the x-coordinate, not the y-coordinate. Because this is sine, specifically, because this is sine that we did the arc sine of, it corresponded with the y-coordinate. So we had to look in quadrants 1 and 2. But since this one here is cosine that we're working with, it would be in quadrants 1 and 4. Now, there's absolutely no way that an angle in quadrant 4 would fit inside of a triangle because that angle has to be between 270 and 360 degrees. So every single angle in quadrant 4 is too big. It's already bigger than 180. So if I do use the law of cosines, the advantage is I don't need to seek a second angle like I do if I use law of sines. All right, I do need my third angle. It is going to be just found from subtraction. I'm going to go underneath just for a little bit of space here. Angle C, 180 minus angle A, which is 30, minus angle B, which was 23.79 or 23.8, however you choose to write that. For degree measures, that's not strictly necessary that you keep more than one decimal place, but I've already done so, so I'm going to just be consistent here with 126.21 degrees. So in conclusion, angle A, 30 degrees, angle B, 23.79 degrees, and angle C, 126.21 degrees. And we've solved this triangle. We found all three sides and all three angles. Now, based on the way that I solved this one, I chose to solve for angle B instead of angle C. This tip at the bottom did not come up for me, but it reminds me that if the cosine of an angle is negative, that's going to indicate an obtuse angle. Had I solved for angle C instead of angle B as my second step, I might have found that cosine of angle C is 126.21. It's negative, of course, right? I ended up with a positive 0.9 because this was not an obtuse angle. But if I was solving this and done angle C, I might have come up with a point here where I had a negative 0.59 equals cosine of angle C. All we want to remember is if that happens, it's absolutely fine to have our cosine be equal to a negative, because for the cosine function, it's positive in both quadrants 1 and 4, and it's negative in both quadrants 2 and 3. And this angle would have been in quadrant 2 because this is an obtuse angle. Okay? So that can happen. That's just fine. Okay, and let's take a look at our next example. Security at the headquarters of Tucky Rigorous Instructional Guides, or TRIG Inc., is being upgraded. A video camera is set up on one wall to monitor a portion of a long hallway. And the viewing angle for the camera is set to be 40.8 degrees, with the distances from the camera to the opposite wall along the edges of that viewing angle being 18 and 12.8 feet. Let's see if we can make a diagram of this hallway. So our hallway is going to have two walls that are perpendicular from each other. We're going to walk down this hallway, and there is a video camera in the corner on one of my walls right here. And the viewing angle for this camera, it's able to see an angle here of 40.8 degrees. And the distances, there we go, I have to get my lines straightened up here. The distances where that opening, my picture is not drawn to scale here, but it's able to see in an arc like there of 40.8 degrees. And the distances that correspond with the edges of that viewing angle are 18 feet and 12.8 feet. So that's a diagram of what this situation would look like for a camera that's positioned here on that side of the wall. Okay, we got our video camera set up on one wall. I put mine here. We've got our video camera, the angle of that 40.8 degrees, and we've got our edges along that viewing angle as being distances of 18 and 12.8 feet. Okay. I just labeled these in this order because it looks like that's the longer side, and it would make sense that the one that's further down the hall would be longer than the one that is higher on the wall. So this is a picture of this situation. Part B asks me, based on the information above, what is the length of the opposite wall that the camera is able to monitor and see to the nearest tenth of a foot? So we're being asked what that distance measurement is. Okay. Let me call this angle A, and therefore I can label this as side A across from it. And then these are going to be sides B and C. Let's go ahead and call this one B. So this will be little b, and this one C. So this will be our little c. Since I don't have any pairings of angle to side, it's a law of cosines situation. And A is what we need to know. So we're going to write this in the form A squared equals B squared plus C squared minus 2BC times the cosine of angle A. That's the version of the law of cosines equal to A squared. So A squared equals B, which is 12.8 squared, plus C, that's 18 squared, minus 2 times our 12.8 for B and our 18 for C, and the cosine of angle A, 40.8 degrees. This is all numeric, so let's go ahead and enter that into a calculator. I'm going to not clear just because I know this calculator is still in degree mode. Won't need to change that. So 12.8 squared plus 18 squared minus 2 times 12.8 times 18 times the cosine of our 40.8 degree angle. See if I can expand that just to make sure everything's typed in correctly. We've got A squared equal to 139.02. And if I take the square root of both sides, we're going to copy paste this number into our square root. We'll get a distance of 11.79, or approximately 11.8 feet for A. We were asked to round to the nearest tenth, so to 1 decimal place. All right. Now the next question asks us to calculate the width of the hallway assuming the hallway has a constant width to the nearest foot. So I'm going to redraw my hallway picture. And I have this triangle. And now I know that this is 11.8 feet. This was 12.8 feet. This is 18 feet. And I knew this angle. That's the 40.8 degrees. What I'm being asked for now is the width. And so the width is going to be the distance across the hallway. It doesn't matter where I put my line for the width because we're going to assume that hallway is the same width. Most hallways are the same width at any point. So I'm going to put it across right here. Now in this triangle, I know that the hypotenuse of this triangle, and I can say hypotenuse because we're assuming this is now a right triangle, that the width would be perpendicular to the length of this hallway. So the hypotenuse of this right triangle is going to be a measure of 18, but I don't know the length of any of the other sides, nor do I know any of the angles. This 18 point, or this 11, I should say, 11.8 does not go the full distance here. And this 12 has nothing to do with this triangle as well. This angle isn't going to help me get this one because there's also this gap up here. However, if I knew this angle, I would be able to find this one as its complement because together these two angles would form 90 degrees. So I'm going to need to find that angle so that I can find an angle inside my triangle and then use a trig function to be able to find the width of this hallway. Finding this angle is a matter of continuing to solve that initial first triangle where we had called this angle angle C. We had our side C up here. And I have a pairing of side A and angle A up here. So I'm going to do a law of cosines on this triangle to find this angle C. So the sine of angle C over the 12.8 side length C is going to be equal to the sine of angle A, which measures at 40.8 degrees, over the length of side A, which measures at 11.8. Multiplying the 12.8 over the sine of C is equal to 12.8 times the sine of 40.8 over 11.8. So I need to come over here. This tells me that sine of C is equal to that product. So 12.8 times the sine of 40.8 over 11.8. Sine of C is equal to 0.7088. And I'll need the arcsine of both sides to solve for C. C is equal to the inverse or arcsine of 0.7088. I'm going to copy and paste that value just to make it easier to enter. Or you can type it yourself. I come up with a C measure of about 45.1 degrees, or any time that we use arcsine, we need to consider the possibility that there is a solution that would have been in quadrant 2. So 45 degrees, or the other possibility for this triangle would have been at 180 minus 45.2, which would have been a measure of 134.8 degrees. Now, I can immediately throw that one away because I know that the angle that I'm trying to find right now needs to be complementary with another angle. And this is already larger than 90 degrees. I can tell that this has got to be an angle that is smaller than 90 degrees. So this possibility is too large. Okay. Now, I didn't even want to know angle C. I want to know its complement. So that's this angle right here. So I'm going to have to call that a new name. Let me just call it theta. So that angle theta is the complement of angle C. So theta is going to be equal to 90 degrees minus angle C, which we've decided was at 45.1 degrees. So they came out really close to being 45, but not, oh, I guess it was 45, whatever it was. I meant to type 0.1 there. My fingers hit the wrong key. I didn't recognize that I did that, so I'll make that adjustment. It's still too big. So our 90 minus our 45.1 puts us just under 45 at 44.9 degrees. In this triangle now, we have our right angle, we have our 44.9 degree angle, and we have our 18 side. What we're looking for is the value across the bottom, which is going to be the width of this hallway. According to this theta angle, I'm going to set up a cosine ratio to be equal to the adjacent side divided by the hypotenuse side. I can use just a regular trig function because there is a 90-degree angle inside of this triangle. Let's set that up. We can say the cosine of 44.9 degrees is equal to W over 18, adjacent over hypotenuse, and therefore 18 times the cosine of 44.9 degrees equals W, the width of our hallway. 18 times the cosine of 44.9 degrees comes out as about 12.75 for the width. And so it's approximately 12.8. I don't know why they said nearest foot instead of nearest tenth of a foot. It doesn't make sense, but we're just going to go ahead and do about 12.8 because that's, we were keeping one decimal place previously. I want to continue to keep about one decimal place in this as well. All right, so the work went a little bit circular on here. We had to first find that angle using law of sines or cosines would have worked. I chose sines. Find the complementary angle, and then I could use a cosine function to find the width of the hallway. Put in a lot of different ideas together in order to find that width. Very cool. Last page in section 8.2, we're going to solve some side triangles. When all three sides are known, the law of cosines is our only hope for solving for a non-right angle. But we must remember that not all side combinations are possible. So we could have no solutions, and we still could have one solution when they are possible. So let's check out these examples. Solve if possible. So I'm going to make a triangle where the side lengths are 2, 3, and 7. Okay, so 2 would have been opposite angle P, 3 would have been opposite an angle D, and Q would have been opposite an angle side of 7. Okay. I can solve for any of the angles. Doesn't matter which one I go for. Let's say I'm going to go for Q. So we'll set this up as Q squared equals P squared plus D squared minus 2PD cosine Q. This is going to be a dyslexic nightmare with these P, D, and Q letters all looking similar, so apologies for those letters there. Q squared, that's 7 squared. P, that's 2 squared. D is 3 squared. Minus 2 times 2 times 3 times the cosine of, I used the wrong case there, angles should be capital, so cosine of capital Q. Okay, so we will subtract over the two measures. And that'll give us 7 squared, so it's 49, minus 2 squared, so minus 4, and then minus 3 squared, so minus another 9, comes out as 36 minus 2 equals a negative 2 times 3 cosine of Q. So now we're going to divide that coefficient, the negative 2 times 3, over. And so we're dividing by 12, right? 2 times 2 times 3. But I'm going to just write it out. I've got myself 36 divided by a negative 2 times 3, which is 12. It comes out as negative 3 equals cosine of Q. Remembering that on the unit circle, the lowest that the cosine value is allowed to get is negative 1. So is it ever going to get to negative 3? No. So this is undefined. So this triangle has no solution. So we saw that warning right away that not all side combinations are possible. If that side length is 7, 3 is not long enough to connect to it. It just doesn't close. The triangle is not possible. Let's look at another one. Hopefully this other one does have a solution, does exist. I've got a really long side length A compared to the others. So this is going to be 11.7. And I've got a shorter side of 5.4. And then a medium side here of 7. So my triangle looks something like this. If that's little a, then that's capital A. Little b, so this is capital B. Little c, so this is capital C. And we can solve for any of our angles. I'm going to go ahead and solve for angle A first. A squared equals B squared plus C squared minus 2BC cosine of A. A squared, so that's 11.7 squared. B, that's our 5.4 squared. C is 7 squared minus 2 times 5.4 times 7 cosine of A. Once again, we're going to take these two terms and subtract them over. 11.7 squared minus 5.4 squared minus 7 squared comes out as 58.73 equals negative 2 times 5.4 times 7 times the cosine of angle A. This is now a product, so instead of subtracting this over, we're going to take this and divide it over. 58.73 divided by the negative 2 times 5.4 times 7 gives us a negative 0.7769 equals cosine of A. We're going to take the arc cosine of both sides. So we'll need arc cosine of negative 0.7769 for A. Arc cosine of, let me copy this number, gives us an angle for A of 140.97 degrees. Remember that if the cosine value is negative, then you must be in quadrant 2. So that means that your triangle is going to have an obtuse angle, which it does, 140 degrees. The other angle would have been in quadrant 3, which is bigger than 180, so that's not a possibility. Okay. I need a little more space so that I'm able to solve for the rest of the things. I have one angle. I already had all 3 sides, so I need to find the other 2 angles. I'm going to make use of the back side of my previous page. If you have room to sneak this in somewhere else, you may try to do that. Now that I know angle A, I have a pairing of an angle to a side. So it is possible for me to use law of sines to find either of my other missing angles, or I could do the law of cosines process again with a different angle. My choice. I'm going to go ahead and use a law of sines, and let's just find angle B next. So I'm going to set up the sine of B over side B, which is 5.4, and then the sine of angle A, which is my 140.97 degrees, over side A, which is the 11.7. So sine of B will be equal to multiplying my 5.4 over 5.4 times the sine of 140.97 degrees divided by 11.7. 5.4 times the sine of that 141.97 divided by our 11.7 gives us sine B equals 0.2906. And to find B, we're going to need the inverse or arc sine of that value. Arc sine of, we'll copy paste just to save time typing that value. And we get a measure for B of 16.89, or technically there's a 6 after that. So I do have to round that to 16.9 degrees if I'm going to keep 2 places, 16.90 degrees. Anytime I use arc sine, I've got to consider both values. So if one of these is 16.9 degrees, the other possible answer would be 180 minus 16.9, and that would be an angle of 163.1 degrees. If B is 16.9 degrees, then the missing angle C is 180 minus angle A, there it is, which was 140.97 degrees minus the 16.9 degrees. I hit the wrong key there, so 140.97 minus 16.9 gives us an angle C measure of 22.13 degrees. And you probably already noticed that the other possibility doesn't work, but we're just going to demonstrate that. If B is 161 degrees, then C would be 180 minus 140.97 minus 163.1. That's definitely going to be negative. So we're going to have no solution from this possible answer here. This would give us a negative 124.1 degrees, which is not possible. So we only do have one possible solution to this triangle. I'm going to write it back on the original paper, although I did my work on this paper down here. That solution is if A is 140.97 degrees, B is 16.9 degrees, and C is 22.13 degrees. I'm not going to write down my 3 side lengths because all 3 of them were already known. So those are just given to me here. And I know all 3 sides, and I know all 3 angles. So this triangle is solved. In conclusion, down here on the bottom of the page, we've got a couple triangles. We want to illustrate the situations and then what law would be needed to solve these. The first case that we looked at was when I knew 2 angles and a side. So if I know 2 angles and a side, in such a way that I've got myself an angle-side pairing, this case here is angle, angle, side, or it's sometimes called side, angle, angle. This is going to be an instance where I can use law of sines. Another situation would be that if I knew 2 angles, but the side I knew was between them, I have no pairing of an angle to a side. This is the case angle, side, angle. And because I've got no pairing where I know both a side and an angle, I'm going to have to use the law of cosines. Okay. Another possible situation, instead of knowing 2 of the angles, I know 1 of the angles, and I know sides that go around that angle. This is going to be the side, angle, side case. In this case, side, angle, side, I don't have a pairing, so that's going to have to be a law of cosines. If I know 2 sides, and the angle that I know is not between them, this is a case that's called side, side, angle, side, side, angle. In this case, the angle is opposite of a side, so that's going to be the case where I can use law of sines. And again, that would also work if I knew this side instead, this angle instead. That'd be across from this one. So anytime I know 2 sides and 1 angle, if the angle's between them, it's law of cosines. If the angle is not between them, it's law of sines. Another case would be that I know instead 3 sides. So if instead I know 3 sides, that's our side, side, side case. There's no pairing in that, so we are going to have to use law of cosines. And any other cases that are solvable. We can solve as long as we know at least one side. So we've got one side and 2 angles. There's 2 ways to do that, 2 sides or 3 sides. I think our third case, or last case, I guess the sixth or the third on this side, would be if we knew all of the angles, and that's going to be not solvable. So if we just know all of the angles, we're not able to solve it. Because if you just know all of the angles, you have no idea on the sides of that. We have similar triangles where the angles are all the same and the sides are all different from each other. There's not one unique solution. So I think those are all 6 possibilities in terms of triangles that we're able to solve for the first 5. And then if you just know angles, you're not able to solve. You've got to know at least one side to solve. I actually want to come back to this one right here. The last thought right here is I know angle, angle, side. I said law of cosines here. I was thinking there should have been one more that was law of sines. It's actually this one could be either. So it's law of sines in that if you know 2 of the angles, can't you find the third angle? We could find B and then do law of sines. If I didn't find angle B, I'd have to use law of cosines.